Almost everything you do online feels wireless. You tap a screen, a message appears, a video starts playing instantly, cloud services respond in milliseconds. It feels abstract, invisible, weightless. But the global internet is not floating in the air, it is physical. At this very moment, more than 95% of all international internet traffic is traveling through cables lying on the ocean floor, not satellites, not radio waves. Cables, thousands of kilometers long, thinner than a garden hose, carrying nearly all the world's data. This is the story of how submarine internet cables are built, deployed, protected, and kept alive, and why their engineering is far more extreme than most people realize. The idea of sending signals through underwater cables is older than the internet itself. In the mid-19th century, telegraph cables were laid across the seas to transmit simple electrical pulses. These early cables failed often. Saltwater corrosion, pressure, and mechanical stress destroyed them repeatedly. But the concept worked. Modern submarine cables operate on a completely different level. Instead of electrical signals, they use light. At the heart of every submarine internet cable are optical fibers, strands of ultra-pure glass thinner than a human hair. These fibers transmit data as pulses of light, bouncing internally through the glass at nearly the speed of light. A single fiber can carry terabits of data per second. A single modern cable can handle more data than entire countries used just decades ago. But the fiber itself is only the beginning. An optical fiber is fragile. On the ocean floor, it must survive crushing pressure, earthquakes, fishing activity, anchors, temperature changes, and decades-long continuous operation without maintenance. So the fiber is protected. Surrounding it is a GL that cushions the glass and prevents moisture penetration. Around that is a plastic sheath. Then comes a layer of steel wires for strength. In shallow waters, additional layers of steel armoring are added. Finally, an outer polyethylene coating seals the cable. In deep ocean sections, cables may be only about the thickness of a hose. Near coastlines, where damage risk is highest, they can be as thick and heavy as a human arm. This design balances two opposing needs, strength and flexibility. The cable must be strong enough to survive extreme conditions, yet flexible enough to be laid gently across mountains, trenches, and plains on the ocean floor. Before a cable is ever built, the route is planned in extraordinary detail. Specialized survey ships map the seabed using sonar. Engineers analyze underwater terrain, seismic activity, volcanic zones, shipping lanes, and fishing grounds. The goal is to find the safest, most stable path possible. Sometimes this means routing cables around undersea mountains or avoiding earthquake-prone fault lines. Sometimes it means choosing a longer route to reduce risk. Once the route is approved, manufacturing begins. Cables are produced in massive factories, often thousands of kilometers at a time. They are coiled carefully into giant tanks aboard cable-laying ships. Any twist, kink, or defect could doom the entire project. Laying the cable is a slow, precise operation. A cable-laying ship moves at walking speed, releasing the cable from the stern. GPS, sonar, and tension monitoring systems ensure the cable settles gently onto the seabed. Too much tension and it could snap. Too little and it could tangle. In shallow coastal waters, cables are often buried. Special underwater plows cut trenches into the seabed, sometimes several meters deep. The cable is laid inside and covered with sediment. This protects it from anchors, trawling nets, and coastal activity. In deep ocean, burial is unnecessary. The depth itself offers protection. At depths of several kilometers, human activity disappears. Pressure is immense, but stable. Once laid, the cable is tested. Light signals are sent through the fiber to check for loss, distortion, or breaks. Only after passing strict performance tests does the cable go live. But even then, the work is not over. Submarine cables require power. Optical fibers transmit light, but that light weakens over distance. To compensate, repeaters are installed along the cable, typically every 50 to 100 kilometers. These repeaters amplify the signal without converting it back to electrical data. Each repeater must work flawlessly for decades. They are sealed units designed to survive high pressure, corrosion, and total isolation. If one fails, repairing it can cost millions of dollars and take weeks. Power for the repeaters is delivered through the cable itself, using a constant electrical current sent from landing stations on shore. This means every cable is both a data system and a power system at the same time. Failures do happen. Despite careful planning, submarine cables break hundreds of times per year. The most common causes are surprisingly mundane: fishing nets and ship anchors. Natural events like earthquakes and underwater landslides also cause damage. When a break occurs, traffic is rerouted automatically through other cables. Most users never notice, but redundancy has limits. In regions with few cables, outages can be severe. Repairing a cable is a massive operation. A specialized ship sails to the fault location. Using sonar and remotely operated vehicles, the cable is located on the seabed. It is lifted to the surface, cut, and repaired. The damaged section is replaced. The cable is lowered back down. In deep water, this can take days or weeks. Weather, depth, and location and all matter. Despite the cost, these repairs are essential. Global finance, communications, cloud services, and national infrastructure all depend on these cables. This dependence creates geopolitical significance. Submarine cables are critical infrastructure. Countries monitor them closely, landing stations are guarded, routes are kept confidential. There are concerns about espionage, sabotage, and surveillance. Some cables are built by consortia of telecom companies. Others are funded by tech giants seeking faster, more reliable connections between data centers. Control over cable routes increasingly reflects economic and political priorities, yet the cables themselves remain largely invisible. They lie silently on the ocean floor, carrying emails, video calls, financial transactions, medical data, and entire digital lives across continents in fractions of a second. Their lifespan is typically around 25 years. After that, capacity limitations or degradation make replacement more economical than maintenance. Old cables may be retired, upgraded, or abandoned. Some are reused for scientific monitoring, others remain on the seabed indefinitely. The environmental impact of submarine cables is surprisingly small. Compared to oil pipelines or seabed mining, cables disturb relatively narrow paths. Marine life often colonizes them. In some cases, they even create artificial reef-like structures. Careful routing minimizes ecological damage. Still, planning accounts for sensitive habitats, coral reefs, and protected zones. What makes submarine internet cables truly insane is not just their scale or complexity, it is their reliability. These systems operate continuously, under immense pressure in complete darkness for decades, with almost no human intervention. A single cable failure could disrupt economies. Yet the system as a whole rarely fails. That reliability is the result of layered engineering, redundancy in routes, precision in manufacturing, care and deployment, monitoring and operation, response and failure. The internet feels abstract, but it is grounded in steel, glass, and ocean geology. Every message you send across continents travels through physical space, guided by human decisions made years earlier. Every video call crosses mountains, trenches, and tectonic plates under the sea. The next time a web page loads instantly, remember this: the signal did not float through space. It raced through a strand of glass, protected by steel, resting quietly on the ocean floor, part of one of the most ambitious engineering systems humanity has ever built.